Now, I would like to welcome Dr. Saeed Alqahtani, who will be speaking to us about radiation safety in overweight patients. Welcome, Dr. Saeed Alqahtani.
Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. And hi again, it's me in the last talk for me today. We are going to talk about obese patient and overweight. And before we get in, how often do you examine or image these patients? 90%, 60%, 80%, 50%? How often do you see these kind of patients in your department? Because these days, overweight and obese became the normal. If you see someone skinny, you say, there's something wrong. Okay? So they became the normal. Not just in this country, in our countries, no, worldwide. It's an international phenomenon. So, my speak today will be different. We will speak science. Okay? So we'll speak instead of going to the clinical practice, I will share with you a research that we did a few years ago to overcome the challenge that we are facing in the radiology department when imaging obese patients. Does it really matter? Yes, it does really matter. As you said, you see almost 70% per day in your department, and they are obese and overweight. So we need to think about them. These are some numbers from the UK and Saudi Arabia as well, for the percentage of obese patients and overweight compared to the whole population. Here, if you look, I'm not sure if the pointer is working, but if you look at the third point, obese patients are receiving high dose, 600% higher dose of air product than DRL in the UK. And this is a study we did in the UK. And we found that obese patients receive almost 600 times the dose received by normal patients. And that's quite a lot. I'm sure this will be in all other country or other country of the world, because they are quite challenging group of patients. Here are two motivations that impose us to do the research. First one, which is a quote from the ICRP 2006 publication, the identification of possible protective options to keep the exposure as low as reasonably achievable, and we all know that, ALARA. Okay? In the second statement, this is a statement by 5 organizations in Europe, and this was one of their strategic goals for the next 5 years, back in that days in 2016. Development of body mass index specific image acquisition protocols. So they want to come up with specific image acquisition protocols for each patient based on the BMI, and a specific dose reduction algorithm for obese patient. And that's why we did this research. So here is tiny quiz. You have a patient, his name is John, okay? And we are going to do abdomen, for example. We need 70 kPb, let's say 70, 35 ms, we'll use copper filtration. The source to image distance will be 1.3 or 1.25. How do you agree with that? How do you agree with that? Do you think it's okay? So what do you do? KVB higher? Okay. Okay. So based on that, John came 2 years later in this shape. What would you do? I need the numbers. Say, let's agree on the first one. John 2 years ago. KVB 70. Do you agree? So 85, 90. So let's say 90. Agree? How much will you give John after 2 years? If we, at the first instant, we give him 90 kVb. Same? Okay. Any other thoughts? Would you go up in kVb or did you go down? Up. So I need to hear numbers because I'm sure there will be a variation. There will be huge variation between us. Someone will say 95, someone will say 100, someone will say, no, 85, it will be enough. So what about MAS? Okay. MAS? Increase. So do you see, there will be a variation between us. So it's a real challenge. It's a real challenge. And what we don't want to, in our practice, we don't want this patient, John, to come to this hospital and get less dose, but in 2 weeks' time go to another hospital and get 3 times the dose that he received 2 weeks ago. That's what we want to avoid, because this is our job, to keep the dose as low as is really achievable. Okay? So it is a challenge. It is challenging. That's why we need to do some work around this area. So these are the studies that we did. First, we looked at the dose from the patient, actual dose. And this is something that you can do. How many of you engaged in research? Could you please raise your hand? How many of you engaged in research, in science research? I'm sure Dr. Abdullah is. I need the audience. Why is that? We work in science. In order to solve a problem, we must solve it scientifically. If we have a family problem, that's fine. We can discuss it with friends, we can try this and that, look, go online and find any solution. But in science, we need scientific steps, scientific methods. So this is something I think it's worth considering doing some research in your department. It's very easy. The first part, dose audit, is very easy. You just collect data from the department for patients who are above 30 BMI. Okay? And then analyze them, very simple analysis. And you will be able to see what's going on in your department. So this was the first study. And that study showed that the dose is 600% more in obese patients compared to normal adults and compared to the national DRL. Then we do some sort of body composition quantification. And because none of you has engaged in research, usually when we talk about dose optimization, we have some sort of phantom, because it's ethically not possible to do or to expose the patient for radiation just for research. Okay? So we can't do that. So how can we do experiments? How can we change the protocols? How can we see what's the effect of these parameters on dose and image quality and so on and so forth? We have something called phantom. It's quite expensive one. It mimics the human tissues when it interacts with the X-ray. Okay? But the problem is there isn't any phantom for obese. There are phantoms just for normal adults. 75 kg weight and 175 height. So we had to get our head around this issue to find the solution. And what we did, we collect data from DEXA scan. DEXA will give us T-score, Z-score. It will give us also body composition to tell us how much fat and how much fat-free or lean mass in that body. So in the second study, this is what we did. We wanted to know how much fat, and we want to know if the fat or if the lean goes up as the fat goes up. And here's a question. What do you think? If you see someone who's quite obese, do you think it's all fat, or is it all lean, or is it both? What do you think? Okay. 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 We found out that it's not just the fat that goes up, but also the lean. And this was quite different to what we knew in the literature. So when we talk about dose optimization in obese patients, we have to add fat, and also we have to add lean tissue, which is muscle. Okay? So does it matter? Why don't we just add fat? And that's it. Because the attenuation is different, especially in low beam energy, 60, 70, 100. Okay? So they will interact with the X-ray differently. The third study we did fabrication. So we built a phantom, and I will show you how we did that. We built a phantom to represent obese patient, different group of obese patients, and then we did the dose optimization. We start experimenting on that phantom. This is the dose audit study. We had around 2,000 patients, data from a hospital. Those patients went to pediatric surgery, and we got the data for them before they did the pediatric. And then we looked at these data, did some analysis, and this is what we found. Look here. If you look at the abdominal AB, the first one, okay? This is the national DRL in the UK, 2.5. This data is driven from UK, okay? 2.5, this is the national DRL, which means any patient who went through abdominal AB, the dose, the DAB, should not exceed 2.5. If it does, then there will be some sort of question. Why is that? Either the machine has some fault in it, either the radiographer is not well trained, or the patient is obese, okay? But they will take it seriously. They are taking the DRL seriously. And the DRL usually, DRL is the third quartile. It's not the average, it's the third quartile. So we compared with the third quartile of the dose that received by obese patient. And this is the number that we got, 17.6. How many times? Almost 7 times the dose. See how much high is that dose? And this is just for abdomen. So these are to compare the DRL compared to the obese patients. There is a huge difference between them, and this is not acceptable in radiology. These are the results. High radiation dose delivered to obese patient. Abdomen and the lumbar spine was the highest, which is normal because they tend to be the most thick parts of the obese patients. There was a limited correlation between radiation dose and the patient size. So it's not easy to correlate between the patient dose and the radiation size, and the patient dose and the patient size and the radiation dose, which means there is a variation. The problem is in the practice. If there is a correlation, that would be clear that if the patient size goes up, the radiation dose will go up. But there was no correlation. There was a little correlation, which means there is a variation. And this is something we need to avoid. We calculated the lifetime cancer risk. There was someone yesterday speaking about effective risk. I'm not sure if she's in with the audience, but this is what we did. We calculated the lifetime cancer risk, and it increases by 153% compared to the normal adults. So, here is the tricky part of the study. We wanted to do something. We know there is a problem, there is a high dose, we need to solve it. We wanted to do some sort of dose optimization experiments. These are the kind of phantom that we have in the market. This is for normal adults. This phantom can be used for dose optimization. It costs around 250 Saudi riyal, 50,000 Saudi riyal. Okay? So it's quite expensive. The problem, there isn't any for obese. So we need to come up with a solution. We did the body composition to quantify, as I said, body mass, the fat mass and fat-free mass. We collected data from 264 healthy female patients. They were healthy. There was no disease on them. And then we did some analysis. We found that fat and lean goes up as the BMI goes up. We come up with some prediction model. So we wanted to have some sort of equation that we can use to predict the fat mass and the lean mass if we want to build our phantom. Here is the third study, which was the fabrication of the phantom. And I think this is it was the best part of the study, even though it took me around 1 year to do it, because at the first instant I failed. And then I repeated, and I finished it in 2 months instead of 8 months. So we want to construct obese phantom that can be used in a dose optimization. The phantom should meet these criteria, should improve on a current commercially available fat addition for phantoms. So we don't want to build it from scratch. We want to add it to something that we have in the market. To be reusable, we want it to be reusable. We want to use it 2 times, 3 times, 100 times, and compare the results, and compare this between scanners and from time to time. We want it must have similar physical and radiological properties of the fat and lean. To be made in-house, because we didn't have that kind of fund to go and buy some sort of expensive materials. So we want something that we can build in-house with the resources that we have and then use it. And this is what we did. We used some sort of materials called urethane-based. That's BMC 121. If you go online, you'll find these materials. Okay? You can buy them, and you can use them. So you can replicate what we did. You can have your own phantom in your department and do some experiments. In order to get a fat mimic, we needed to add 2.2% of phenolic microspheres to make the density of these materials a bit low, below 1. And to mimic lean mass, we added 2.8 of calcium carbonate. And then we tested these materials for physical density to match it with fat and lean. We did house field unit to make sure that it's exactly the same house field unit for fat and lean of a human. We did attenuation coefficient to see if it attenuates the same amount of X-ray as the fat and lean does. So this other phantom that we had, this is the one that is on the market. So this one can be bought online. So this is Tokyo phantom. The Kyoto phantom.
Sorry,
we
Doctor.
Scanned it.
Sorry, Doctor, 5 minutes left.
Okay. So we scanned it, and then we did a bitmap to make a mold for the phantom construction. I will just skip these steps here because the result is at the end. So this is the phantom that we built. If we look here, this is representing BMI of 18.5, which is the normal one. And then we add some sort of layers that represent fat and then lean as well here. So we come up with a series of phantom starting from 18.5 BMI to 46 BMI. We used a Siemens X-ray machine. And we used some sort of factorial design research method, where we have different variables with different levels. So we used KVB and SID and filtration. But KVB we used 70, 75, 80, 85, 90, 95. Okay? So this is called factorial design. We came up with around 360 images. We analyzed them subjectively and objectively, and this is what we got. this is the effect of the KVB on the dose and the image quality. This is the image quality, and this is the dose. Okay, and we can see that as we use low KVB, we got high dose, but at the same time we got low image quality. Sorry, we got high image quality, but high dose with 70. As we go down, the image quality will drop, the dose will drop, as we expect. This was the SID. It didn't have that effect on the image quality or the radiation dose. And this was the filtration. We added some filtration, and this was the 0.3 did the best when it's come to dose, because as you see here, it reduced the dose, but when you look at the image quality, there wasn't much reduction in the image quality when we use 0.3. Okay? Look at this. This is for the first phantom. If we look there, the best parameters was 70 kVb with filtration. This is the first phantom. Second one, again, 75, and the filtration is 0.3. Third phantom, again, 70, 75, and 0.3. And this is the last one. We couldn't use the filtration because the filtration will absorb most of the beam, and also the patient will absorb a lot of the beam, so we couldn't get any image. So this was the prediction model that we come up with. So if you use this model precautionally, this will be valid only on the machine that we use. So you can predict how much MAS you need to give to the patient based on this equation. So MAS equal 270 minus 27.9 multiplied by the thickness of the patient, okay, plus 0.825 multiplied by the square of the patient thickness. This is to predict the MAS that we need to give to the patient. So the final result, or the final take-home message that we can take from this lecture is the third one. KVB and filtration are the most effective parameters in dose optimization in this group of patients. And if you look there, back in the result that we got, we used 70 and 75. We didn't go that much up. Because if we go up, we will increase the scattered radiation. DR are very sensitive to scattered radiation. So the noise in the image will be high, the quality will degrade. Okay? So use the restrainer that you have in the department. The best are the filtration. The only issue with this measure, it will degrade the time life of the machine. Because if you use filtration before the patient, that means you need a lot more high beam energy. Okay? So think about this in your department. Also, you have to know the cutoff point of your machine, because it will get to a certain amount of MAS and it will cut off. So it will stop working. So think about that when it comes to obese patients. Thank you.